And also I'll give you a copy.
Yeah.
All right. So let's start with the permutation groups. So that's our topic of discussion today.
Yeah.
You know, you really need to understand permutation groups for you to be able to find out if there is an isomorphism between S4 and D12.
Mm.
Yeah. So what is a permutation group?
Hmm. Mm.
So you can think of,
yeah, hold on. Yeah. Permutate. Is that something that go in circle and repeat himself?
Okay.
And if it tends to be a group, it needs to follow the same property of the group.
Yeah. So if you think of words and letters, I'm going to pick a word. Yeah. And I'm going to pick 3 letters, M, A, D, right?
Yeah, yeah.
These are 3 letters, and then we need to form different words, okay? We can form different words by rearranging the letters, okay?
Yes.
So you could say that I'm not going to do anything, do nothing on the letters, and your word is mad, right? And then you could decide to keep the M, just switch the A and the D, and then you can have MDA.
Yeah.
Right? You could also have AMD. You can also have DAM, DAM. You can also have MDA. Which are the what? 1, 2, 3, 4, 5. DMA, right? Okay.
Yeah.
So, in short, to permute is to rearrange. And when we started out with the letters MAD, we came up with the different arrangements of these letters, and we formed a group. So instead of the letters MAD and the words, if we translate these to numbers, let's say you have the numbers 1, 2, 3.
Yeah.
You could decide to do nothing and form 1, 2, 3, right?
Yeah.
You could decide to flip them and form something like 2, 3, 1, 2.
Yeah, 1.
Right?
Yeah.
Could form a word like 3, 1, 2. That rearrangement, meaning that 1 has gone to 3, 2 has gone to 1, and 3 has gone to 2.
Yeah, like we were doing in that triangle.
Yeah, like we were doing with the letters.
Yes.
And then which other one can we do?
We can do 1, 3, 1. No. 1, 3, 2.
Okay, just 1 sec. Let's have 1, 2, 3 going to 1, 2, 3. Then we can have 1, 2, 3 going to 3, 1, 2.
Yeah.
Right? We can also rearrange the 1, 2, 3 and move to 2, 1, 3.
Yeah.
Right? We can also have the 1, 2, 3 being taken to
1, 3, 2.
1, 3, 2. We can also have 1, 2, 3 being taken to
Sorry, it's my wife saying goodbye.
Oh, it's okay. So 1, 2, 3 can go to 2, 3, 1.
Yeah.
And then 1, 2, 3 can go to
Hold on.
3 to 1.
3 to 1.
You see? And I think that's the only 1, 2, 3, 4, 5, 6. I think these are the only permutations that we can get from the letters 1, 2, 3. That's the only way we can do it. So you could think of this as a function, right? So if this is a group, you could think of this map, it's a function. You could call this something like F1, taking 1, 2, 3 to 1, 2, 3. You could assume this is F2.
F2.
This is another function F3, another function F4, another function F5, and another function F6.
Yes.
Right? So the binary operation in this case, so the binary operation star is a composition of functions.
Okay.
Composition of functions. And we are saying this because the group S3 is going to be a group of functions. You see, one element is F1, which happens to be the identity. And then we have F2, F3, F4, F6, F5.
Yeah.
Okay. Yeah. So to make our work easy, we usually use what we call cycles.
Yeah.
So for example, you can see that F1 is doing nothing. So there is no way we can have a cycle in F1. That's the identity, right? But consider F2. Let us think of these functions as cycles. So what is F2 doing? It's taking
1 to 3.
1 to 3, right?
Yeah.
And then it's taking 3
2 to 1.
3 goes to 2, right?
Yeah, oh, 3 goes to 2, yes.
And then 2 goes to?
2 goes to 1.
2 goes to 1. So this is the function F2.
Yeah.
That's what it's doing. It's taking 1 to 3, 3 to 2, and 2 to 1. And so as a cycle, you could think of this as 1 going to 3, 3 going to 2, and 2 going to 1.
Yeah, I'm close.
Yeah. So this is the representation. This is the representation of the function F2 as a cycle.
Okay.
Yeah.
That's fantastic. Yeah.
Okay.
Very good. Yeah.
So, can you think
this
of
way? Is just take in your mind straight away.
Yeah. So think of this cycle 3, 2, 1.
Yeah.
Is it not the same cycle?
3, 2, 1. It looks like the same in
it's
such
the
a
same
way.
Cycle, right?
Yes. Yeah.
Think of the cycle 2, 1, 3. Is it not
2,
the
1,
same
3.
cycle?
2, 1, 3. Yeah, it looked like the same in the reverse way.
Yeah. So because you see 2 goes to 1, 1 goes to 3, 3 goes to 2. It's the same cycle.
Yes.
So that is why whenever we are creating a cycle representation of one of the functions, we usually call it the rule of the thumb. Rule of the thumb. Because we have so many representations, choose the one starting with the smallest number. Okay, smallest number. Okay. So let us do an exercise. So we had.
Hold on. Let me take the note. Yeah.
Okay.
Yes, thank you.
All right. So for the first one, we have F1, we have F2, F3, F4, F5, and F6. And we already said that F1 is going to be the same as, F2 is going to be the same as the cycle 1, 3, 2.
1, 2, 3, 4.
So what is the cycle representation of F3?
Two, 1, 3.
Okay, let's start with F1, sorry.
Okay. The cycle representation of
F1.
is
1 goes to 1.
Yeah,
The cycle stops.
Yeah.
Okay. 2 goes to 2, and the cycle stops.
Oh yeah.
3 goes to 3, and the cycle stops.
Yes.
So the representation for F1 is going to be 1,
yes,
2, 3.
Yeah.
So F1 is like a composition of 3 cycles that are doing nothing.
Yeah.
Yeah. Okay, so let's look at F3.
F3.
Yeah, we think of it as a cycle. What is its cycle representation?
1 goes to 2.
Okay,
2
1
goes
to
to
2.
Yeah, and 2 goes to 1. This is one cycle.
So 1 goes to 2.
Yeah, and 2 goes to 1.
That's one cycle.
Close. Yeah, and 3 goes to 3.
3 goes to 3.
Yeah.
So for F3, whenever we have like a cycle of length 1, we just ignore it. So you could say this is a cycle, 1 goes to 2, 2 goes to 1, and 3 goes to 3. So instead of writing that 3 goes to 3, we just assume it.
Yeah.
Because you see, as far as 1 goes to 2 and 2 goes to 1, and the cycle says nothing about 3, it's assumed that there was no change on 3.
Yeah.
F4.
F4, 1 goes to 1. This is one cycle. And then 2 goes to 3, and 3 goes to 2. We close it.
So there is no change on 1, but the 2 and 3, they are switching position.
Yes.
F5.
F5, please, let's see. F5. F5. 1 goes to 2. 2 goes to 3. And 3 goes to 1. It closes the cycle. So
1 goes to 2. 2 goes to 3. And 3 goes back to 1. F6.
F6. 1 goes to 3. 2 goes to 2. We close it. And 1 goes to 2. 2 goes to 3. We close. 2 goes to 2. And 3 goes to 1.
And 3 goes to 1. So this is 1, 3.
Yeah.
And nothing happens to 2. Okay.
Hold on. Let's see again. Yeah. 1, 2, 3. Oh yeah, 1 goes to 3, 3 goes to 1, and 2 is okay.
Yeah. So we can represent S3 in this case as this group. So this is going to be the identity. And then you have 1, 3, 2, 1, 2, 2, 3, 1, 2, 3, 1, 3. Okay.
Yeah, so 1, 2, 3, 4, 5, 6. Okay. So F1 is identity.
Yeah.
Yeah. Okay.
Yeah. So S3 is a group with 6 elements.
Yeah.
So in general, we say that the order of Sn, that is the number of elements inside Sn. When you look at 3, 3 is the same as, when you look at 6, 6 is the same as 3 factorial.
Yeah.
So we usually say that the order of any symmetric group with n elements is going to be n factorial.
N factorial, yeah.
Yeah. So if somebody was to ask you, what is the order of S4?
Yeah, 4 factorial.
And what is 4 factorial?
4 times 3, 24.
24.
Yeah.
So S4 is going to have 24
elements.
24 elements.
Mm-hmm.
Yeah. All right. Next, some few definitions.
Yep.
Definition one. A cycle of length 2 is called a transposition.
Okay. A cycle of length 2 that has 2 elements.
Yeah.
Mm-hmm.
It's called a transposition. Second note, you need to note that every permutation is a product of disjoint cycles. So let's confirm that. Let's see, is this true? Mm-hmm. Let us take.
Yeah, please, the note, write it properly.
What?
NO, note 2.
Yeah.
Yeah. The O doesn't show properly.
Wait, what did you say?
On the note, note 2. Yeah. The N of note doesn't show properly.
Oh, you cannot see it?
No, I cannot see note. The O on the note.
Oh, okay.
Yes.
All right.
Yeah.
I think it's good now.
Yes, very good. So that if somebody want to know properly, yes.
Yeah.
Yeah, every permutation is the product of disjoint cycles.
Yep. Every permutation is a product of disjoint cycles.
Disjoint cycles. Yeah.
Yeah. So let us check that using S3. Let us take 2 disjoint cycles, 1, 2, and 1, 3. Right?
Yeah.
Let's see what they are going to produce. So here we know that 1, 2, 3. The function F2, the function 1, 2 means that 1 goes to 2, right?
Yeah.
1 goes to 2, and then 2 goes to 1, and then 3 remains. right?
Yeah.
And then if we do 1, 3 on this, it means that 2 remains, and then 3 and 1 switch position, right? Hello?
Yeah. I'm not getting the second cycle.
The second
Is it
cycle?
through F? Yeah.
You see,
1 goes to 2, 2 goes to 3, and 3 goes to 1.
okay, no, this is not a cycle. These
Okay.
ones, they are not cycles. Let me, okay, maybe I'm using the wrong notation.
Okay.
So I have my numbers 1, 2, 3, right?
Yeah, yeah.
And then 1, 2 is the function F3.
Yeah.
Composition.
Yeah.
1, 3 was the function F6.
Okay.
So I was asking myself, if I was to compose these two functions,
Yeah.
what function would I get? And so I picked my elements 1, 2, 3. And then I did an F1. I did an F3 on 1, 2, 3. But 1, 2, 3 is not the cycle. It's the elements in.
Okay, yeah, yeah, I see. Yeah.
So 1 will go to?
On F3. F3. 1 will go to 2.
And 2 goes to?
2 goes to 1.
And 3 goes to?
3 goes to 3.
And then you do the second function, F6. 2 goes to?
Oh, yeah. Okay. F6, 2 goes to 2.
2 goes to 2.
Yeah. 1 goes to 3. And 3 goes to 3.
And 3 goes to 1.
Oh, 3 goes to 1, sorry.
Yeah. So question is, which is this function that takes 1, 2, 3 to 2, 3, 1?
Okay.
It takes
we need to look at the
1 to
function
2,
and yeah.
right?
Say that?
It takes 1 to 2, right?
Yes.
The function takes 1 to 2.
Yeah.
So as a cycle, it's going to be 1 to 2. And then 2 to 3.
2 to 3.
And then 3 to 1.
Yeah. 3 to 1. Yeah.
So a composition of 1, 2, 3 and 1, 3 gives you 1, 2, 3.
1, 2, 3. Yeah.
Which happens to be the function F5. Right?
Wonderful. Yes.
So I was just trying to show you that every permutation is a product of disjoint cycles.
Yeah.
I took is a product. No, it's a product of disjoint transpositions. This was very wrong. Sorry.
Sorry.
Transpositions. So I took one transposition, a cycle of length 2, another cycle of length 2, and see what I got. I got F5.
Yeah. Cycle of length 3.
Yeah. Now, can you express? Let me take F2. Can you express F2, which happens to be the cycle 1, 2, 3, as a product? Can you express F2 as a product of disjoint cycles?
Yeah, we can have 1 to 2 as one cycle and 2 to 3.
1 to 2 as one cycle, and 2 to 3 as the other cycle?
Yeah.
Okay. So 1 goes to 2, 2 goes to 3, so 1 goes to 3, and then 3 goes to 2, and 2 goes to 1. F2,
Yeah.
oh wait, F2 was 132. Let me correct this. Nice, 132. So that is another property of symmetric groups, that if you want to come up with a cycle, if you want to come up with any cycle, you can just get transpositions and get every other cycle in the group, right?
Okay.
Yeah. I have been thinking about generators of S4.
Okay.
And how to get them, the structure of S4. Because remember the question we wanted to answer, we wanted to see if S4 would be isomorphic to D6, right?
Yeah.
So let us come up with S4 and try to figure out its behavior.
Okay.
Yeah.
So S4 means that we need to have a set with 4 elements, like 1, 2, 3, 4.
Yeah, like 1, 2, 3, 4.
And do the permutation.
Yeah. Okay, maybe before we go there, can you give me the order of F2? What is the order of 1, 3, 2?
The order of 1, 3, 2, 1, 2. The order is it 2?
The order of 1, 3, 2. It's the number
order
of
is
times.
not. It's not the number of elements, isn't it?
No, it's not the number of elements. It's the number of times you compose F2 by itself to get the identity.
Okay. Yeah. Yeah, I need to work this out.
Okay.
So, have we done 1, 2, 3 before?
Not really, but it's isomorphic to D6.
I think that the order.
No, it's isomorphic to D3.
D3. So it means that the order between these two will be 2 and 3.
Yeah.
Yeah. So here is 3.
The order of 1, 2, 3 is 3.
I think so.
The order of E, 1.
Is 1.
The order of 1, 2
is 2.
2. The order of 2, 3.
2.
The order of 1, 2, 3.
3.
3. And the order of 1, 3.
2.
Do you think there is a relationship between the length of a cycle and its order?
Yes.
That's a mathematical feeling that I got. We should go out there and research. Actually,
yes.
Let me make it.
That's assumption.
Yeah, let me make it.
We need to prove it.
Yeah, a topic of something you should prove. So is there is there a relation between, we can as well do it now, between the length of a cycle, the length of a cycle, and its order. So let's try to see if it's going to be the same for S4, okay?
Yeah.
Because we can only get the generators of F4 if we come up with a strong conjecture.
Yeah.
So S4, let us try to construct it. So we can partition, so S4 is permutations of permutations of the set 1, 2, 3, 4.
Four.
We could decide to come up with partitions. You could decide to come up with partitions. I'm just trying to cut a corner because I'm not willing to come up with 24 elements.
Okay.
So I will make partitions and I will say, if you think of this as letters and you want to make a word, I want to make a word with only one letter. Okay. How can I do that? I can only make, I can only partition my letters as 1, 2, 3, 4, and I can only have one way of doing that. And this cycle is going to be the identity.
Yeah.
Okay. Let's say I want to make another partition, but now this time I want to have let me have a word with, I want to have one word with one letter, one word with another letter, and a third word is going to have 2 letters. I'm thinking of this 1, 2, 3, 4 as letters, and then you know, you can come up with words. We usually come up with words using letters. Okay.
I'm not getting it.
Okay.
The partitions 1, 1, 1 that generate 1, 2, 3, 4 is one identity. I know. Why are you having only 3 boxes?
You see, I have 1, 2, 3, 4 numbers.
Yeah.
And I wanted, here I have 3 boxes because I want to permute 2 numbers out of the 4 numbers.
Okay.
And now I'm asking myself, how many permutations will I get out of that? Remember, we are talking about permutations of the numbers 1, 2, 3, 4, right? We know there are going to be 24 of them, but now we are coming up with a way of doing it.
Okay.
So the first way I decided to create to permute just one letter. And I realized there is no way I can permute 1 when it's alone.
Yeah.
Okay. Yeah. So if we want to have permutations involving only 2 letters, you could say 1, 2, right?
Yeah.
That is 2 going to 1 and 1 going to 2.
Yeah.
You could also have 1, 3, right?
Yeah.
You could also have 1, 4. Okay.
Yeah.
You could also have 2, 3, 2, 4, and 3, 4. 1, 2, 3, 4, 5, 6. 6 transpositions making up S4,
Yeah.
right?
Yeah.
What is the other way we could do it? We could come up with 2. I could divide it into 2. So I still have my 4 letters, but I want to switch to exactly 2. Okay. I think if I do the example, you're going to see what I mean, because saying it is becoming difficult.
Yeah.
So
That's
I
what
could have,
they call it abstract math.
yeah, I could have 1, 2. I could take 1, 2 and switch them. And then at the same time, I take 3, 4 and switch them. And this is going to be 1 permutation. Maybe to illustrate, to help you see what I did, I have 1, 2, 3, 4. But now I decided to deal with 2 letters at the same time. So I decided to take 1 to 2 and 2 to 1 and stop. And then I go 3 to 4 and 4 to 3 and stop. And then write this as a permutation. And you could think of my box like this. I decided to cut the 4 letters into groups of 2, and then I try to permute them.
Okay. Okay.
I could also do 1, 3, 2, 4. Right?
Yeah.
And then I could also do 1, 4, 2, 3. And I'm going to have 3 of this. 3 elements.
Okay.
So how else can we do it? Can you try coming up with the next way? You see, in the second group, I decided to take a group of 2 and 2 different groups of 1. In the second one, I took 2 groups with 2 elements each. I'm partitioning the set. So whatever I'm doing here, it's partitioning the set.
Okay. So we can take 2 elements which are different, maybe 2 and 3.
But if we take 2 and 3, it means we should have 5 elements in S4, but we don't.
Okay. Yeah. Okay. So 1 and 3.
Very good. 1 and 3. Meaning
or
that
3 and 1. Yeah.
Or 3 and 1. It's the same thing. So what does it mean? We are just using 3 words. We are just using 3 numbers to permute. We are just permuting 3 numbers, and then we are ignoring 1 number. So this means you are permuting 3 numbers, but the 1 number is somehow ignored because there is no way you can permute a number that's alone. So how could you permute 3 numbers? Create a cycle from the set 1, 2, 3, 4.
1, 2, 3.
1, 2, 3. So 1 goes to 2, 2 goes to 3. Very good.
2, 3, 4.
2 goes to 3, 3 goes to 4, 4 goes to 2. Perfect.
2, 3, 1.
2, 3, 1 is the same as 1, 2, 3. That's a repetition.
Okay, we don't repeat element
Yeah.
in one set.
Yeah.
So
It's not that we don't
what?
repeat.
Yeah,
It's not that we don't
1, 3, 1.
repeat. Uh-huh.
Yeah, 1 to 4.
1 to 4, very good. You see, I can repeat the 1, 2, 3, but I'm not going to say 1, 3, 2. Oh, I'm going to say 1, 3, 2. Do you realize these are the same letters, but the two cycles are different?
1, 3.
You see, in the first
Is
one,
it
1 goes to 2, but in the second one, 1 goes to 3. So they are different.
Yeah.
You know, the other one you said, I rejected the 2, 3, 1. I rejected the 2, 3, 1 because if you think about it, 2 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1. 1 goes to 2, 1 goes to 2. It was the same.
Yes, exactly.
Yeah. So you can repeat the numbers, but the order really matters, how you are doing it.
Okay. So the next one could be 1, 3, 4. Is it there?
1, 3, 4. Perfect.
4, 2, 3.
Okay, 4, 2, 3. The rule of the thumb, start with the smallest number. I wrote somewhere some rule of the thumb. You're always advised to start with the smallest number. So when you say 4, 2, 3, I'll take that 4, 2, 3. That is the same as 2, 3, 4, and it's there.
2, 3, 4 is there. Okay. Yes. How many elements do we need?
8. 1, 2, 3, 4, 5. 3 more.
3 more.
What is the inverse of 2, 3, 4? Do you know how to pick an inverse of a permutation by instinct?
No.
The inverse of 2, 3, 4 is going to be 2, 4, 3. If you switch these two numbers, then you're going to get a completely different permutation, and it's going to be the inverse of this. Okay.
How can I make my screen big? Okay, is it?
It's big now.
Yeah. The inverse of
2, 3, 4 is 2, 4, 3.
2, 3, 4 is 2, 4, 3.
The inverse of 1, 2, 3 is 1, 3, 2. So if you've gotten that pattern, you are now able to get the two remaining cycles.
Okay. The inverse of 1, 2, 3
is 1, 3, 2.
1, 3, 2.
And it's there.
And we got it. We got this one, this one. So the inverse of 1, 2, 4.
Yes.
Is 1, 4, 2.
Very good. That's the other cycle. One more to go.
And we got 1, 3, 2. The inverse of 1, 3, 4 is 1, 4, 3.
Perfect. And these are 8.
Yeah.
Elements. 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 plus 3, 11 plus 7, 20. So we need 4 more for S4 to be complete. So how are we going to partition it?
Okay. We got 4. One, two, 1, 2, 3.
So we already did 1, 1, 1, 1, 1, 2,
Yeah.
2, 2, 1, 3. So the next
3,
thing,
1 is the same.
uh-huh.
I was saying 3, 1, is it the same as 1, 3?
Yes.
Okay.
So just don't partition. Don't partition.
Okay.
Just
Yeah.
get the 4 itself. So you just come up with one partition with the 4 elements. You see, this was 2 partitions with 1 element and 3 elements, 2 partitions with 2 elements and 2 elements. This was 3 partitions with 1 element, and 2 elements. So you can just come up with 1 partition with
of all 4.
Yeah. And so what would be the cycles? You could have 1 goes to 2, 2 goes to 3, 3 goes to 4. That's 1. The other one?
1 goes to 3.
1 goes to 3.
3 goes to 4.
3 goes to 4.
And 4 goes to 2.
And 4 goes to 2.
1 goes to 4.
1 goes to 4.
4 go to 3.
4 go to 3.
And 3 go to 2.
3 goes to 2. Next one.
1 go to 3.
1 go to 3.
3 go to 2.
3 go to 2.
And 2 go to 4.
2 goes to 4.
Okay, I think we finish with the ones. So 2 go to 1.
2 go to 1.
1 go to 3.
1 go to 3.
3 go to 4.
Go to 4. So the rule is always to start with the smallest. So this should be 1, 3, 4, 2. It's there.
It's there.
Yeah.
Yeah, it's there already. So it's finished then.
Have we? I don't think so.
So 1 go to 2.
1 go to 2.
2 goes to 4.
2 goes to 4.
And 4 goes to 3.
4 goes to 3. 1, 2, 4, 3. Okay. Next one.
1 go to, I'll say 4.
Okay.
4 goes to 1. No. 4 goes to 2.
2.
And 2 goes to 3.
2 goes to 3. 1, 2, 3, 4, 5, 6. Oh, I guess that's it.
How many have you got in total?
This is 6. 6 plus 6 is 12. 12 plus 8 is 20. 20 plus 3 is 23 plus 1, 24 elements in S4.
Okay.
Yeah. You know, coming up with the 24 elements is not easy. And that is why we partition. That is the sole purpose of partitioning. Okay. Now, there was this conjecture that we are still working on. Do you think the order of 1, 4, 2, 3 is 4? 1, 4, 2, 3. Is its order 4?
Yeah.
Because we thought about
S3.
yeah, we saw that in S3, and then we came up with a mathematical feeling, and we should look into it. So 1 goes to 4, 4 goes to 2, 2 goes to 3, 1 goes to 4, 4 goes to 2, 2 goes to 3. So this is going to give you 1 goes to 4, 4 goes to 2, so 1 goes to 2, right?
Yeah.
And then 2 goes to 3, 3 goes to 1. So 2 goes to 1. And then 3 goes to, no, 3 goes to 1, 1 goes to 4, so 3 goes to 4. And then 4 goes to 2, 2 goes to 3. So we have that, right?
I'm not seeing it perfectly.
Okay. So we're supposing these two.
Yeah.
1 goes to 4, 4 goes to 2, right? 1 goes to 4 in the first one, 4 goes to 2 in the second one. So the result is 1 goes to 2. There you go.
Yeah. Yeah.
And then 2 goes to 3 in the first one, 3 goes to 1 in the second one. So 2 goes to 1. And that's a transposition.
Yeah.
And then we ask ourselves about 3. 3 goes to 1 in the first one. 1 goes to 4 in the second one. So 3 goes to 4. And then we looked at 4. 4 went to 2 in the first one. 2 went to 3 in the second one. So 4 went to 3, and it became a transposition, 3, 4.
Yeah. Yes.
You've seen it now?
Yes.
Okay.
Thank you.
You're welcome. Okay, so let's keep going. We are looking for the order of 1, 1, 4, 3, 2. So let's multiply again by 1, 4, 2, 3, right? So this is going to become 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes to 4, 4 goes to 2, so 3 goes to 2. 2 goes to 1, 1 goes to 4, so 2 goes to 4.
That's what we want.
What?
No, not yet. We need the identity.
So let's do another one.
Yeah. 1, 4.
So this was the first one, the second one. Now we are in the third one, right?
Yeah.
4, 2, 3. What do we get? 1 goes to 3, 3 goes to 1.
Yeah.
Okay. So 1 goes back to 1.
Yeah.
2 goes to 4, 4 goes to 2. So 2 goes back to 2.
Yeah.
3 goes to 2. 3 goes to 2, 2 goes to 3. So 3 goes back to 3. 4 goes to 1, 1 goes to 4. And this is the identity.
Yeah.
So we just found out that this was a squared. A squared gave us this, right?
Yeah.
And then we multiplied by a, so this was a cubic, which gave us this, and this was a power 4. So the order is indeed 4.
Yes.
We have done it 4 times to get 4. Okay.
Yes. Yes.
So go out there. Go out there. So go online, because
Yeah.
this is a very solid. It's my feeling. I spent my time looking for evidence.
Yeah.
I spent my time looking for evidence because I knew that for us to come up with good isomorphisms, we must find out about the generators.
Yeah.
So go out there, look for a theorem to support our work, because I think it's an assumption that we can use.
Okay. So you haven't seen a theorem yourself?
What?
Have you seen a theorem, or we can assume is it and then trying to demonstrate?
I haven't seen a theorem myself. So I was looking for it before you came in, because I already had this conjecture yesterday. And so I was looking for the theorem, because, you know, once you get a conjecture, you must go out there and look for a theorem. Okay.
Yeah.
So if the theorem is there, which I believe most probably it's going to be there.
Yeah.
Yeah. Okay. First of all, we already did for S3, the 1, 2, 3, the 2, 3, 4s and everything. These ones, they were of order 3.
Yeah.
So maybe you can do another experiment. If you do 1, 3, 2, 4, is it going to be of order 4?
Probably. Okay, so we cannot conclude now. When I have time, I will check it and find out maybe on my notes.
Yep.
If there is such of theorem. Yeah.
Okay. So let's go back to our question. The question was, is D12 isomorphic to S4? So D12 is going to have an identity, and then it's going to have a generator A, and this generator is going to have order 2. It's a reflection.
Yeah.
And then it's going to have a rotation B, which is a rotation 30 degrees rotation, meaning that you can do that rotation to get to 60 degrees. You can do it again to get to 90 degrees. You can do it again to get to 120 degrees. Do it again to get to
150.
150 degrees. Do it again to get to
180.
180. Do it again to get to
210.
Do it again.
That's B8.
Do it again to get to 240.
Yeah.
Do it again to get to
270.
270. Do it again to get to 300 and no, to get to 300.
Yeah.
And then do it again to get to 330. But if you do it again, it's going to take you back to E.
Yeah.
I hope you can form the mental image of the shape that we are rotating.
Yeah.
And then you're going to have a rotation, no, a reflection and a rotation. That's another reflection.
Yeah.
We saw that last time.
Yeah.
A reflection and a rotation. a reflection and a rotation, 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 a reflection and, okay. So D6, D12 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 reflections. So it has 12 elements of order 2, because a reflection is an order 2.
Yeah.
These are reflections. Okay.
Yeah.
And so it has 12 elements of order 2. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's going to have 11 rotations. The order of B is 12. The order of B squared is 6. So this one has order 12. This one has order 6. This one has order 4. This one has order 3. This one has order 12. This one has order 2. This one has order 12. This one has order, I don't know. No, this one has order 3. This one has order 12. This one has order 8. No, 4. This one has order 4. This one has order 6. Okay. So basically, this is the structure of D12. Okay.
Yeah. D12.
This statement, the fact that we have 12 elements of order 2 is enough to show that there is no isomorphism. Right? Because if we come up to S4, how many elements do we have of order 2? 6.
Yeah.
So they are not similar. You know, for you to have an isomorphism, everything has to be similar. So for the number of elements, both of them had 24 elements. So their cardinality was the same.
Yes.
But when you look at the elements of order 2, in S4, we got 6. In D12, we got 12 elements of order 2. And that is enough to show you that there is no isomorphism.
Okay.
Yeah.
Let's see the number of elements of D12 again with 2 elements. Okay.
So D12 has 12 elements of order 2. S4, S4 has 6 elements of order 2. Right? So D12 has 1, 2. Actually, 12 elements of order 2, it wasn't 12, it was 12. There was this one. It was actually 13. Because it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I counted it? Oh, sorry.
Which one?
11, 12, 13. It was 13, yeah. elements of order 2. There is this one.
30.
This one.
Which one? I can't see.
A.
Yeah.
B6.
Yeah.
And these ones, all of them.
AB square, and such as such.
Yeah. Yeah. Okay. D12 has 2 elements of order 6. 2 elements of order 6. Okay.
Yeah.
But S4 has no element of order 6. S4 has no element of order 6.
Yeah.
So there is no isomorphism between S4 and D12/24.
Okay.
No isomorphism at all.
No.
Yeah.
Because the structure need to be the same.
Yeah.
Okay.
So the date today, the date today was 21st February.
Yeah.
And let me send you your notes. These are not my notes, they are yours.
Thank you.
All right. So how did I write the others? Algebra 21/2. Oh, okay. Not valid. Let me see. What did I do?
Maybe the forward flash.
Oh yeah. So I think, so whenever you want to show that there is isomorphism or no isomorphism, you just check the properties.
Yeah.
Yeah. So the number of elements. So first of all, you check the number of elements. If the number of elements is not the same, then you can conclude that there is no isomorphism. But if the number of elements is the same,
yeah,
then you have to go on, look at the orders of the elements, their behaviors and everything, and see if you can have such an isomorphism. So if you find that the orders don't match for the two groups, then there is no such isomorphism.
Okay.
Yeah. All right. So that's it for today. You can go back to Preply for confirmation. And
for
also,
yeah, I will. Yeah, we can book another session.
Yeah, we can book another session, and also you can let me know what you want us to do tomorrow. So you said we could just study groups using your notes, or you could send me a question that is going to help us break things down. So if you don't have a question, do you have a question that we can discuss tomorrow?
Yes.
Okay, you're going to send it on my email.
Yes.
Yeah.
Yeah. Okay.
All right.
Yeah. So what time tomorrow?
Any open slot on my schedule? Let me see. I think tomorrow, same time. How about tomorrow, same time? If you want.
Yeah, it'll be good.
Okay, same time will be good.
Yeah.
Okay. Yeah.
Yeah.
If you want to go somewhere during the day, I think I'm also available at night.
At night.
Yeah, so that is if you want to do something during the day. Let's say you want to go somewhere.
Yeah.
Yeah.
No, tomorrow. No. Nothing so far.
All right.
Unless there's an emergency.
Okay. So
Yeah.
I'm going to schedule same time tomorrow.
Yes. Mhm. I don't need to confirm, isn't it?
Yeah, you need to confirm today.
Okay.
Yeah.
So you are sending me the copy and the recording, or?
Yeah, I'll send you a copy of the recording.
Mhm.
Yeah. Also I can send you a link. If I post it, I can send you a link. Hello?
That's great.
Yeah.
Are we still recording?
Yep. Let me stop.